A combustion blower is not selected by burner kilowatts alone. The right question is, can it deliver the required oxygen-bearing air at every firing rate while overcoming the complete air path resistance? Too little air can create unstable or incomplete combustion. Too much air wastes heat and can move the burner away from its commissioned ratio. Let us build a selection that an engineer can actually review. Start at the burner, not the blower catalog. Map the air train from the room inlet through the filter, silencer, duct, blower, control damper or valve, flow device, burner register and burner head, then into the furnace or boiler pressure. On a forced draft system, the blower supplies the pressure rise that keeps this entire path moving. A fuel valve meters fuel on a separate rail. The burner management system must keep those two rails safely coordinated. First, establish combustion airflow. Use the burner manufacturer's air demand data across its full firing range whenever it is available. If you must calculate a starting point, derive fuel flow from the real heat input and fuel heating value, use the correct stoichiometric air requirement for that fuel composition, then apply the specified excess air target. Correct for inlet temperature, altitude, humidity, and any air preheat. Combustion depends on oxygen mass, so a volume copied at one density is not automatically valid at another. Here is an illustrative screen. Suppose the burner schedule requires 75 cubic meters per hour of air at the defined reference condition. Add the pressure losses at high fire, 100 pascals for the inlet and filter, 200 for duct and fittings, 250 for the metering damper, 1000 through the register and burner head, 150 for the maximum positive chamber pressure, and 200 for the agreed dirty condition allowance. The required point is 75 cubic meters per hour at 1900 pascals. Use calculated or supplier pressure drop data, not these example values. Now put that single point on a tested fan curve at the stated speed and air density. The operating point is where the fan curve meets the system curve. A maximum airflow number at zero pressure is useless here, and shutoff pressure at zero airflow is not the duty point. On this LONGWELL LWGE148S-05 graphic, the curve shape is a useful reading exercise. The region near 80 cubic meters per hour and about 2000 pascals is close to our illustrative target. That makes it a candidate for detailed review, not an approved selection. Do not stop at high fire. Plot light off, low fire, normal fire, and high fire. Confirm the blower, damper, and control method can reach each point without unstable fan operation, motor overload or loss of air to fuel control. A 4-to-1 burner turndown does not mean a 4-to-1 blower speed command. Pressure losses change with flow, the register may move, and the control curve must be commissioned against measured air or flue gas results. Then challenge the density cases. Cold dense air carries more oxygen per cubic meter and usually requires more fan pressure for the same volume path resistance. Hot, high altitude or preheated air carries less oxygen per cubic meter, so the required volume may increase. Convert on a mass basis and apply the fan manufacturer's correction method. State whether the schedule uses normal cubic meters, standard cubic feet or actual inlet volume. That small line prevents a large error. Next, verify the physical blower. Check that the wheel and housing provide the needed pressure in a stable region. Confirm absorbed power, maximum speed, voltage, frequency, start frequency, control signal, feedback, motor protection, and acceptable sound. Also define inlet cleanliness, ambient temperature, altitude, moisture, corrosion, vibration, mounting position, connection loads, and service access. A fresh air combustion blower is not automatically suitable for hot flue gas or contaminated recirculation. Margin needs engineering, not a blanket percentage. Put filter fouling, chamber pressure variation and ambient extremes into separate system curves. A little defined reserve can be useful. An oversized blower forced to throttle continuously may waste energy, reduce controllability, and still fail the low fire requirement. Select across an operating envelope, then show where the control device and motor limits sit on that envelope. Finally, preserve the combustion safety chain. The air-proving device must confirm airflow or pressure before fuel is enabled. The required purge sequence, ignition trial, flame safeguard and safety shutoff valves belong to the listed burner or furnace control design. If airflow is lost, the fuel safety valves must close according to that design. Never tune around an interlock, and never treat blower capacity as a substitute for combustion commissioning by qualified personnel. Before release, send one review sheet: fuel and heat input, required air at every firing state, reference density, complete pressure loss ledger, chamber pressure range, candidate fan curves, speed and power limits, control and feedback, materials and environment, purge and interlock requirements, dimensions and connections, and the test plan. Validate the final assembly with the burner supplier and applicable codes. Need that duty point review for your burner air train? Send the schedule to longwellfans.com/contact.